When we are doing property-based testing of some function, then we call this function on a randomly generated input. The question is, if we don't know what the input of the function is, how do we know what the output should be? Now, typically, the way that we solve this problem is by having some sort of reference implementation, right? Some other implementation of the same function that computes the same result, but maybe it's very inefficient, very slow, uses lots of memory, all kinds of stuff, right? All kinds of things that don't matter for the test as long as it gives us the same result so that we can test our real function. Often, however, such a reference implementation might not be available. Maybe it's too expensive, like in terms of manpower, to develop. The question is, how do we test functions in such a situation if we don't have a reference available? And that's what we're going to talk about today.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, this show is live streamed. We invite you to submit questions or comments in the chat, and we will try to show them on screen and to discuss them.
Right, so as an example to test something, to have something to test, I want to talk about finding the shortest path between two nodes in a graph. This is an algorithm that we talked about in the previous episode of the Unfolder, which you can watch if you want to. But for this episode, we don't care how it works. We just care that it exists and that we want to test if it works. We're going to treat it as a black box. We don't need to know how it works. But it's a good example of the situation that I described in the introduction, right? Suppose that we have a random graph, some graph that we don't know, and we ask for the shortest path, and we get some path back. How do we know if that's the right path? Now, of course, if we don't do property-based testing, but we do unit testing, then we don't do this at all, right? We come up with some graphs, we call our function on it. Since we know what graph we're giving it, we know what path we expect, and then we can just check it. Now, unit testing has its place, but it has two important downsides, maybe more, but at least two. One is that the number of examples that we can test is necessarily quite small, right? Because we have to write them all by hand. And second, if there is a bias in your thinking that, for example, you're forgetting some edge case when you're implementing the algorithm, you're very likely to have the same bias also when coming up with examples. True story, when Anders and I were preparing for the previous episode and we were working on this algorithm, our algorithm actually had a bug in it for a while that we did not know about and did not realize. And there was an edge case that we were missing. The edge case was that if the graph had some disconnected component somewhere, the algorithm would crash. And typically, as is typical, the examples that we work with also did not have disconnected components, right? It's the same bias. So that's why we want to typically do property-based testing to solve this problem. Rather than working with graphs that we know, we generate random graphs, and then we call the algorithm. But like I said, if we generate a random graph, how do we know that the path that we get back is the right path if we don't have an alternative implementation of shortest path? So that's what we want to work towards in this episode. Now, to get started on something slightly simpler, in order to do this, we need to generate random graphs, right? That's a key ingredient. And just to get us started, one of the things that we're going to have to do is generate random cost. So just to remind everybody what shortest path does is we have a graph of nodes. There's edges between these nodes, or vertices, right? Every edge has a cost associated with it, or a length. And we want to find the shortest path between two edges, two vertices in the graph. So if we generate a random graph, we're going to have to generate random costs, right? That's just as a something too simple to start with. Let's think about this first. Now, the choice of data type that we have for cost matters, right? I mean, I'm going to choose int here, which is possible. But for example, if our algorithm would have problems with rounding errors, right? If we were to choose floating point, then choosing cost to be integer means that we would not find such problems. And so the choice here has ramifications. But for the sake of today's presentation, I'm going to choose int. Okay, now we need to generate random costs. And to do that, we need
two remarks. I mean, one is I think you're not showing the entire module today, right? You're hiding some pieces of code, like up there, for example, the imports.
A whole bunch of imports, yeah.
Yeah. So that's one thing. And the other thing is we are doing this in QuickCheck, right?
Oh, yeah. Thank you for reminding me. Yeah, that's true. Yeah. There's many ways to do property-based testing in Haskell. The two main libraries are QuickCheck and Hedgehog. And there's a third contender, which is my own library called Falsify, that we have an
We also
episode about.
already talked about, yeah.
Yeah, exactly. We have an episode about that. But yeah, quite right. For today, we're going to talk about quick check.
Yeah.
Okay. So, right. We have made a choice of how we are going to, what we choose for cost, and now we need to write an arbitrary instance for cost, which means we need to say, how do we generate random costs? And we're going to do this very simply. To generate a random cost, we are simply going to choose a value between 0 and 100, and that is going to be our cost. Very, very simple. Now, the other thing that we need to think about when generating values is that we need to shrink values also. What does that mean? Often, when we are randomly generating some input to a function, we might generate a large value. Maybe it's a graph, right? Maybe we generate a very large graph. And if our function fails on this large graph, we should shrink it, right? Because typically, if the graph is very large, maybe lots of parts of this graph are not relevant to the problem, right? And if we don't cut this out, then we have a very arduous debugging task ahead of us. Right, so we typically want to have a counterexample to a property which is as small as possible, that has only necessary detail and nothing else. And we do this by implementing a shrinker. And the shrinker just takes a value, in this case it's the cost, and then should give you a smaller cost. Now in this case, we're just going to piggyback on the shrinker for integers. So we're just going to shrink C. This gives us back all the ways that we can shrink C, and we just wrap them again in cost. Right, so this is our arbitrary instance. Okay. And now as a first property, one of the things that the algorithm depends on is that when we're looking for a shortest path, it can't happen that by adding another edge to our path, by making the path longer, the overall cost shrinks. Right? That is something that the algorithm depends on. If we would have edges with negative cost, that might be the case. Right? But so this is something that the algorithm depends on. So let's test that this is in fact the case. Right? If we have two costs, C1 and C2, then we want to know that C1 plus C2, if we add some other cost to it, it should be it should be less than or equal to it, right? Now, the other thing that's useful often in properties is that if a property fails, we might want to give some additional information about it. And in this case, for example, if this fails, it might be useful to know what the sum actually is. Mm-hmm. Okay.
You don't have num and ord instance.
Oh, yeah, sorry. Now I do. Okay. Mm-hmm. Okay. So we could test this by running this. And if we do that, it says, okay, all tests pass. Mm-hmm. Now, just to show, suppose that I flip this around. Right now, this is a bug in the test, but then we get a counterexample, and it tells us a couple of things. It tells us it picked 0 for C1, it picked 1 for C2, and then this is the additional information that we added to the counterexample, right? Which is C1 plus C2, which is also 0 plus 1 equals 1, right? And 0 is not greater than or equal than 1. So this is a counterexample. Mm-hmm. And we can also see that these values are very small, right? So it's shrunk them to the minimal values. Yep. Okay. Good. That was by means of warm-up. So now let's think about graphs. In the episode that we had, where we just talked about the algorithm, this was the representation of graphs, right? So we had a bunch of vertices, then a function that, given a vertex, gives us all the neighbors, and then a final function that, given two vertices, gives us the cost of the edge between those two vertices. Now, this is a useful representation for that particular algorithm, but it is not a useful representation for testing, right? Because for multiple reasons, but for one thing, if we can't show these graphs, right? We can't show functions. And if I come up with a counterexample, but I can't tell you what it is, that's not a particularly useful test, right? So we want a representation of graphs that is showable. And the other problem is that it's hard to inspect, right? We can't shrink such a graph. Like we can't easily remove an edge from it or things like this. Right? So this is not a particularly useful representation. We want something more concrete. Now, the exact choice that we make here is not really all that relevant and it's kind of beyond the scope of this episode. But just to have something to work with, we're just going to represent the graph as a map from pairs of vertices. So these are the edges in the graph to their cost. Mm-hmm. right? So then the set of vertices is just implied, right? If there's an edge between two vertices, then the vertices are, like those two vertices must be in the graph. Right? So this is a very simple representation, maybe suboptimal for many cases, but this is just for demonstration purposes.
Yeah, I think as I said last time already, I mean, graph representations are always suboptimal for some use cases. So
Right.
I mean, it is a totally normal thing that you have
Right.
several different ones between you
Yeah.
sometimes have to
Yeah.
convert. Yeah.
So there's some additional code in here that I'm not going to talk about at all. Feel free to browse it. There's a Git repo with all this code. Hopefully the details will become clear as we talk about it. Okay. We need a representation of vertices in the Anderson's code from last week. That was just polymorphic. So we're just going to make a choice here. And I'm going to make this choice. So the first 5 vertices, we're just going to call 8 up to E. And then after that, we're just going to number them. And it's just to make sure that small counterexamples have nice, easy to read examples, easy to read vertices here. Okay. We were going to find it useful to have a list of all vertices. So that's just this, right? Okay. Now we need to generate arbitrary graphs. So let's talk about that and let's see how to do that. And I'm going to copy and paste the code in here. This is something that I should mention in this episode. Like typically we do live coding in these episodes, but testing requires a bit more bureaucracy, a bit more infrastructure to set things up. So I want to explain the intuitions and the concepts, but not necessarily all the details. So that's why I won't be live coding today.
But the code is available after
yes.
the episode in the usual place
yes.
in our GitHub repo. Yeah.
There should be a link in the video description. Okay. So how are we going to generate a random graph? The first thing to note here is that as QuickChat generates examples, it tries to start small and then works its way up to larger examples, even though we have shrinking available as sort of an independent way to get smaller examples. And so we want access to the size, the current size, and we do that by calling this function size. So this is the size parameter from QuickChat. It tells us we should roughly generate something of this particular size, whatever that means for your particular example. So we're going to choose between 0 and size vertices. This is how many vertices we want in our graph. Now, one thing that's useful to note here is that when we generate graphs where we can choose from lots of vertices, and then we generate random edges between them, we're quite likely to generate graphs with lots of disconnected components, right? If we have, instead, choose from a very small set of vertices, we're much more likely to generate graphs with lots of connected components. So actually, it is quite useful and important that we choose a small number of vertices most of the time. Okay, so then the vertices are just the first num vertices from this list here. Okay, easy enough. If there are none, if we chose none, then we just return the empty graph, right? We can't generate any edges between empty vertices. Otherwise, we pick a number of edges, and we want more edges than vertices normally, so we just multiply it by some random factor. In this case, I chose 10. And then we just repeat an action, which is going to generate a random edge. How do we do that? We pick 2 random vertices, which are the starting and end point of this edge. We generate a random cost, and that's our edge. Of course, it might be that we happen to generate multiple edges between the same 2 vertices, and we just filter those out, choosing just the first one. Okay, that's it, right? This is the generator for arbitrary graphs. I'm going to leave out the shrinker for a bit and just talk about the property first. So we now have a random graph, and we can ask Dijkstra's shortest path algorithm, what is the shortest path in this graph? And it's going to give us an answer. Right? It's either going to say there's none, or it's going to say here is a path, and it's the shortest one. Now, we can't really easily verify if it is indeed the shortest, although we will see ways that we can close to that. But one thing that we can at least easily check is, well, if it tells us that there is a shortest path, then that path should be a valid path in the graph, first of all. And if we trace that path ourselves, we should find that it has the cost that the algorithm tells us it has. Right? If that's not true, then the algorithm is horribly broken. Right? It's giving us nonsense answers. So let's write such a property first. I'm just going to call it valid, like it gives us valid answers.
Yeah, you're saying it as if it is so nonsensical, but it's very tempting to implement a shortest path algorithm that just always returns 0.
Well, if you're such a lazy programmer, then maybe yes.
Yeah.
But yes, indeed.
Yeah.
Yeah. I mean, of course, it is quite possible. If you have bugs in the algorithm, that it generates, invalid paths,
Yeah.
right? That's not at all unlikely. So this is a useful property to have. It's a useful starting point for sure. Okay, so we have a random graph, but now we also need 2 vertices in this graph, right? Our starting and endpoint for our path.
Yeah.
And the problem is we could pick those randomly, right? For a random graph and 2 random vertices in this graph. But this is introducing a dependency, right? Because those vertices are chosen from the graph. Now, if we start shrinking this graph, maybe we remove some edges from this graph or some vertices from this graph, maybe the 2 vertices that we picked are no longer valid, right? So there's a dependency between these 2 things, which is possible, and we'll see an example of that too. But if you can avoid it, it's always better, easier. You avoid difficulties that way. And if you think about it, actually, we don't really care. We could just always pick A and B, right? The first 2 vertices, because we're generating some random graph. A and B sit somewhere in that graph. It doesn't really change anything if we always pick A and B as the 2 endpoints for our path, right? I mean, the algorithm is polymorphic. It's unable to inspect the vertices, so it doesn't really.
The one situation you're then never testing, I'm just thinking, is that like the source and the target may be the same, right?
The same,
and
yeah, that's true.
That is actually exhibiting a bug. But I mean, you could write a separate property just for that.
Yeah, that's true. Yeah, absolutely. Yeah, that's true. Yeah. Okay. So we're going to have some random graph GR, and we're going to call the algorithm, and the algorithm is going to give us some information. We don't really care what that is. It's just what the algorithm returns. We need to translate our graph representation to the representation that the algorithm uses, right? I've called this to Dijkstra, and a starting point, and we're going to call this A. And we want to know the path from A to B. Now we do need to know that A and B are in the graph. Right, so if that is not the case, if the graph is so small that is not the case, we're just going to say, okay, discard this test. And so we're going to say that on the assumption that the graph has vertices A and B, do something. So this will mean that if quick check will verify this, and if it says, okay, actually the graph you generate does not have these, it will just try again. It will just try it with some different values. Okay. So what is the property? This looks a bit complicated, but that's because there's a couple of cases to consider. First, we're going to ask the algorithm, did you find a path at all, and what is its cost? Now, if the algorithm says, no, I did not find any path, then we just have to go shrug and say, okay, that might be the case, right? We have no evidence to say that there's a path between A and B. Maybe that's true, right? So in this case, we're just going to say discard, okay, meaning skip this case, right? We're not, for the sake of this property, not important. Now, if the algorithm tells us there is a shortest path and this is its cost, right, then we can add some additional information to our output if we find a counterexample. Then we can ask the algorithm, okay, what is the path, right, between these 2 things? Before it just told us the cost, now we want to know what is the actual path. And if that fails, now we do have this is a failure, right? This is a bug. If the algorithm tells us there's a path and here's its cost, but then it's unable to tell us what the actual path is, that will be a bug, right? That will be a problem.
Yeah.
So that's a failure, test failure. Okay, so we now have a cost and a path, and we can add that information again to our counterexample if there is one. Now we can just check, okay, what is the cost of this path in our graph, just computing it ourselves, right? And if we say, actually, this is not a valid path, then again, we have found a bug. The algorithm has told us something that is invalid. And if we do get some cost, then the cost should be equal to the cost that the algorithm told us. Right, so this is just doing a sanity checking. If there's a path, then let's verify that the path is correct and that it has the cost that the algorithm says it should have. Okay, so we can test this.
Right, and it looks a little bit more complicated than it perhaps needs to look, but it's very nice to use this counterexample to give meaningful feedback in the case something is going wrong, as you're demonstrating here.
Yeah, all of these calls are optional. Yeah.
But it makes the failure much easier to read in the case that it occurs.
Right. Yeah. For debugging, this is very useful.
Yeah.
Okay. So now we've established that the algorithm does not give us nonsense answers. That's good. It's a good starting point. Now let's move on to actually testing that it is the shortest path. Okay, how do we do that? How do we, like, if we have no way of computing the shortest path, how do we know that it is the shortest path? Now, one way to say is that actually it should be shorter than every other path, right? Okay, you might say, okay, well, yeah, duh. But if you think about something like this property here, right? It says for all costs C1 and C2, right? Some property should hold, right? We have some sort of universal quantification. How do we implement universal quantification? By random generation. And so we can apply that insight to say, well, for all paths in a graph, meaning for all randomly generated paths, right? That's
between
how
these two vertices.
Between two vertices, yeah. The length of the path that we randomly generate should be greater than or equal to the shortest path, right? We should not be able to randomly generate a path that is shorter than the shortest path that the algorithm computes. So let's do that. Now, this is an example of where we really have a dependency, right, that we cannot avoid. We have a graph and a path in a graph, and we want to generate these together and maybe also shrink them together, right? If we, yeah. But let's talk about the shrinker separately. But let's first talk about this path and graph thing here.
But your definition now is motivated by wanting to shrink properly, right?
Yeah, I'm defining this as a single data type that has both things in there, so that when we come to shrinking, we can also shrink them together. Yeah, that's right. Okay, so a path in a graph is simply a graph and a path in that graph. Okay. How do we define this guy? Well, first we need to be able to generate random paths. Okay, that's quite easy. We have some graph and some starting vertex v and a length of the path that we want. And how do we do it? Well, if we want a path of length 0, we're done. We just return the empty path or the path containing just the vertex, that's our starting point. Otherwise, we find all the neighbors of the vertex. If there aren't any, then there's no way to continue the path, right? So we just also return the singleton path here. Otherwise, we pick a random neighbor and then recurse, right? So we just start with this and then recurse with the smaller length. Okay.
Okay.
Relatively simple. So now how do we generate a random path and a random graph? Well, we generate a random graph using the arbitrary instance that we already have. And we want a graph that is not empty, otherwise we can't generate any paths in it. Then we pick a random starting point. We pick a random length. Then we generate a random path using the function that we just defined, and that is our result, right? A graph and a path. Okay, good. So now we can define a property that we wanted. We can say that the shortest path should be shorter than every other path, right? Whereas between two vertices, right? Where every other is going to be implemented as randomly generated. So here's the property. We have a random path in some random graph. And now we do the same thing. We ask Dijkstra, what is the distance of the shortest path? And if Dijkstra says nothing, it says, I can't find any paths. Now we know that can't be the case, right? Because we have a path in this graph, right? So we know that we have evidence that such a path exists. So if Dijkstra can't find it, that's a counterexample, right? We have a bug. If it does find it and it tells us some cost, well, then the cost that Dijkstra found should be smaller than or equal to the length of the path that we have. Okay.
And let me just re-emphasize, I mean, counterexample, the function does not mean that we are in an error case, right? It just adds information. I find that slightly counterintuitive.
Yes.
It's the false. It's the fault, the fact that we are just like returning false. That means,
this should be called like add info or something. Yeah, I agree. Yeah, it's a confusing name. Yeah, that's true. Okay. So this is a much more direct definition of the property that we really want to test. So let's verify it. And it says it passed all tests. That's good.
My algorithm is good.
Yeah, that's reassuring. So now let's actually add a bug into the algorithm, right? So let's maybe say that we so somewhere in the algorithm we have an update to we're computing basically the distances and the path separately. So if we compute the distances but not the path, then
Don't update the predecessor. So.
wait, this. Oh no, it's the validity now that breaks. Sorry,
Yeah.
I should now go off script. Let's think of an.
Yeah, this should violate the validity.
Yeah.
Although, yeah, I could the.
Yeah, I think. Let's see if this.
Just crash in that case.
Yeah. Yeah. Okay. Good.
Yeah.
All right. Okay. Yeah. Sorry. So this is the case. This is the edge case that I mentioned at the start of the episode, where we might deal with graphs that have some unconnected components, right? Some graphs, some nodes that we can't reach at all. Right? So this is what happens here. Now we get a counterexample, which is good, but the counterexample it's kind of complicated, right? It's not too complicated, but it's more complicated than it needs to be. We have some complicated costs here. We have two edges here, whereas actually a single edge would suffice. Right? This is not a very good counterexample, right? Why is the cost 1881? Is that relevant? Why does it have to be 1881, right? It's like a red herring. And if I run it again, here, this is even more complicated graph. Like we have some path that visits itself many, many times, right? Where we have three edges here, right? The counterexamples that we're getting here are too large. They have detail that are not relevant to the particular problem that we're dealing with. So to fix this, we need a good shrinker. We need to shrink both graphs and paths in graphs, right? And actually, a benefit of the representation that I chose is that shrinking is actually relatively simple, right? How do we shrink a graph? Well, we have a bunch of edges. We can either one or two things, right? We can either just drop some edges from the graph or shrink one of the cost of the edges, right? That's exactly what this thing is doing here. Two edges and from edges is basically just wrapping, like Newton wrapping. And here we have the actual thing. Shrink list either drops an element from the list, which in our case means dropping an edge, or shrink an element in the list, which in our case means shrinking the cost of an edge. Okay. So really quite simple. And then how do we shrink a path in a graph? Well, we now have two things to shrink, right? A graph and a path. It's important that we shrink them independently, that we don't try to shrink them both at once. That's a common mistake in shrinkers. But actually, that's very, very simple to do. How do we shrink a path? Well, we either shrink the path. We do that by dropping either a prefix or a suffix of the path, and then we leave the graph alone. Or we shrink the path, shrink the graph, drop some edges from the graph. But of course, if we drop an edge from the graph, it might well be that our path is no longer valid, right? So we're saying here, shrink the graph, but only insofar as you can shrink it whilst keeping the path valid. So what this means is that if we do want to shrink both, maybe we shrink the graph a bit, we shrink the path a bit, we shrink the graph a bit, right? We go back and forth between shrinking either one. And that's so important. And that's why it's so important that they are defined together. Otherwise, that would not be possible. Okay, if we now rerun, we get a much, much nicer counterexample, right? We have exactly one edge with cost 0, because the cost is irrelevant, and a path with just one node, right? Completely unnecessary. All unnecessary detail is gone.
Yeah, we have one question, and even before that, I mean, perhaps a short remark. If you just like show the command again that you've run on the command line, so you're actually specifically selecting, in this case, the shortest property as a test case, right? So it's only running that one. I mean, that is always so quick. I just wanted to
sorry.
that again because there was a question
Yeah.
about that. The other question that we should be discussing, or is perhaps a suggestion more, is by Niklas. Could we also start with a random path and then somehow randomly construct a graph around it, where we know by construction that the initial path is the shortest?
Yeah. That is certainly possible, and I think that's a very nice segue to the next section of the episode. And I know that we're already at 30 minutes, and we might be a little bit run a little bit over time. I hope that's okay. But yeah, this is a very important way, right? If I can generalize Nicholas's question here, is a very useful way to test such function is that, okay, we don't know what the input is, right? A random graph. But maybe we can have some manipulation of the input, some changes to the input, and we should be able to predict how those changes influence the result. For example, if I find the shortest path in some graph, and I add additional edges into this graph, then I can only make the situation better, right? It should not be possible that I then find a longer path, right? So that is something I can state. And this is called, John Hughes calls this metamorphic testing. And by the way, there's a reference here to an absolutely fantastic paper by John Hughes called How to Specify It, where he talks about all this material. He doesn't use the example of Dijkstra, he uses trees, but nonetheless, this is, you should definitely read this if you haven't already done so. Okay, yeah, so let's take this idea, metamorphic properties. And I want to show two, and I'll go relatively quick, but I think the idea is relatively simple. So the first one is exactly what I just said. If I start with some graph A, and I look for the shortest path in A, and I have some path, like if there is no path, then that might be the case, right? There's nothing we can say. If we then add some additional edges into this graph, and I look again for the same shortest path in this larger graph, and I then get Dijkstra saying, actually, I can't find a path. That's a bug, right? We know that by adding edges, we cannot make it impossible to find a path. And moreover, the cost of that path can only be smaller, right? It could be equal or smaller, but not larger, right? So this is an example of we modify the input in some way. In this case, we're adding additional edges, and then we're making predictions about what how the output changes. So this is a very useful technique. Now I want to show one more example of this. And one thing that's a little bit unfortunate about this particular example is that we are still saying something relatively vague, right? The cost should be less than or equal, right? It would be nice if we could say something more precise. So one thing we could do is, suppose that we have two graphs and they're completely disjoint. And I find a path in the first graph from A to B. And then I add an edge from B to the starting point in the second graph. And then the shortest path there, right? Then if I add all three together and I find the shortest path in this full graph, that should be exactly equal.
To the sum of
the sum, yeah,
things,
exactly.
To the sum
yeah,
of
exactly.
Yeah.
Right, exactly.
Yeah.
So that's what I can implement here. I have two graphs, A and B, and I insist that both must have vertices A and B. Now, they might not be disjoint, but we can make them disjoint by simply mapping a function over the edges, right? So I'm mapping left. We're using polymorphism here, right, to take advantage of this. We're mapping the left constructor over the left graph and the right constructor over the right graph. So now these are graphs where the edges are no longer vertex, but either vertex, vertex. Okay, so by definition, they must be disjoint. So then we can union them and then add the additional edge, right? So we have a path from left A to left B, from left B to right A, and then from right A to right B. Now, if I ask Dijkstra for the shortest path in both my source graphs, and that there is such a path in both cases, and I then ask Dijkstra for the shortest path in the combined graph, then the cost of that combined path should be exactly equal to the shortest path in the left graph, the edge in the middle, and the shortest path on the right. Right, so that's another way that we can talk about. It's similar to Nicholas's suggestion, right? Like we're constructing graphs in which we know the answer of some in some way or form. Okay. Yeah, that's all I wanted to say about this topic. Like I said, there is many more things that we can say about this. Do read John's paper. And if there are any other questions, we should.
I don't see any further questions right now, but I have one more question myself. And I mean, I think you have nicely demonstrated sort of the general techniques that one can apply in order to come up with plausible properties, and in particular this metamorphic testing seems to be like really cool. But is there anything that you can do in order to get an idea whether you've done enough? Like whether you are in any sense exhaustive, or whether you've covered enough, or I don't know. Is there some guidelines you can give with respect to that?
Yeah, that's a tough one. I think that depends on the application. I think when it comes to trees, I think John makes an argument in the paper that by having a certain set of properties, you're sort of fully specifying what you mean, like when an algorithm is correct.
Mm-hmm.
I don't know if such a complete specification is possible for a shortest path algorithm. I would have to think about that. Yeah. Do you have any thoughts on this yourself?
No, I mean, nothing beyond what seems relatively trivial. I mean, you can certainly try to see, like, have you kind of, have you covered all the corner cases? Are there any natural properties like with relations between the inputs, relations between the outputs that you obviously have not yet been exploiting? Are there other functions that you can relate the whole thing to? Like, does it distribute over something else, or these sorts of techniques? But really, like, being exhaustive is difficult, right? I mean, like if you're not really going into the area of like completely specifying the algorithm somehow, like having a complete specification somehow, it's probably going to be difficult.
Yeah, I think if your property is compositional, you might have a better chance, right? If a property is compositional and you can show that all the different ways that you can build up your data type, all the different ways that you can construct a tree or whatever, all preserve your property in some way, then you might have a chance at completeness. I think for graphs, this is non-compositional, right? If I add two graphs together, which are not necessarily disjoints, then that might change the answer completely. Like, it's not easy to define it in terms of the two components. That makes, I think, giving a complete answer quite difficult.
I mean, there are certainly many situations in which you might still be able to make some statements, like the one that you did in your last property, right? I mean, you could conceivably generalize that somewhat, and then still make some statements. Like, if you know the shortest path and two subcomponents, and you know something about the way these two graphs are connected, then perhaps, but again, I don't know. Did you actually run these? I mean, do we know that they're correct?
I did run them. Here we go.
Okay, all right.
So maybe a final remark here is that if we look at these, like, we have quite a few discards, right? Like, we have 100 tests, but 130 tests were generated that we discarded. In general, discards make testing more costly. But I would say like a 1-to-2 or a 1-to-1 ratio like we have here is fine. It's not a big deal. Like, if you're discarding too many tests, then at some point QuickCheck is going to give up and say, like, I don't know, I can't generate more tests. And then you need to be cleverer about how you generate your test, and you can't do stuff like this. But for applications like this, or with ratios like this, it's fine.
Yeah. Okay.
All right. Okay. Well.
Yes.
Yeah.
Yeah, thanks for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe, and feel free to leave further comments in the comments below the video. We'll just leave the chat open for a few more minutes, and we'll be back in hopefully 2 weeks. Thank you.